Let us now observe some different and standard loci, different locus of different concepts. What are they? First of all, amplitude of Z is equal to pi by 4. You need not use pen and paper for this. Let Z is equal to x plus iy. Amplitude of Z is tan inverse y by x. Tan inverse y by x is pi by 4. Y by x is tan pi by 4. Y by x is 1. X equal to y. Hence, the locus of this is the line passing through origin and bisecting first quadrant and third quadrant. Locus of Z such that amplitude of Z is equal to pi by 4 is the line, x is equal to y. So whenever different loci are asked, you try to convert Z in terms of x plus iy or in the mod amplitude form, so that you will be able to have the locus. Moreover, find the locus of Z such that amplitude of Z is equal to pi by 4 and in the positive region only. If we add some other information, then the locus is a ray starting from origin and which is being expanded in the first quadrant, like that. In the positive region only, both x and y are positive, he says, then it lies in the first quadrant only. Like that you may have to imagine. Amplitude of Z is equal to pi by 4, and suppose he may ask you amplitude of Z is equal to say pi by 3. What is the locus of this? Tan inverse of y by x is equal to pi by 3. That is y by x is equal to tan pi by 3, that is root 3. Y is equal to x root 3. Hence it is a straight line passing through origin and inclined at an angle root 60 degrees with the positive x-axis. That is x-axis in the positive direction. If he doesn't give you any further information, you leave the locus like that. You leave the locus like that. Next one. Modulus of Z minus Z1 is equal to modulus of Z minus Z2. What is the locus of Z? What is the locus of Z? I'm not giving you any numbers. I just give you Z1 and Z2, general complex numbers. What will be the, Z1 and Z2, any given complex numbers. Z is the arbitrary complex number. If mod Z minus Z1 is equal to mod Z minus Z2, like that, if it is given in the data, how can you trace that result? What is the locus of Z? What is the locus of Z? Look here. Let this be Z1, let this be Z2, and Z is a complex number. Z is a complex number which moves at an equal distance to Z1 and Z2, isn't it? Observe the diagram. What is the distance? Mod Z minus Z1. What is this distance? Mod Z minus Z2. Mod Z minus Z2. So this distance and this distance are equal. What does it mean? The complex number Z, whose locus is supposed to be obtained, moves at an equal distance between Z1 and Z2. It is just nothing but the perpendicular bisector of the segment joining Z1 and Z2. You must be knowing that. You must be knowing that. As an example, let me illustrate this. Modulus of Z minus 3i is equal to modulus of Z minus 4. Then the locus of Z is, or Z lies on, he gives you some of 4 options. He gives you some 4 options. What is the locus of Z? How to trace the answer immediately without any unnecessary calculations? Z minus Z1 is equal to Z minus Z2. It is just nothing but the perpendicular bisector of the segment joining these 2 points. What do you mean by 3i? What do you mean by 3i? 3i is the complex number 0, 3, isn't it? 0, 3. And what is this complex number 4? It's just nothing but 4, 0. What is the perpendicular bisector of this? What is the perpendicular bisector of this? You just calculate. That is just nothing but the locus of z required. And it is, you are well versed with the procedure of finding the perpendicular bisector from the knowledge of coordinate geometry, of course. You just find the perpendicular bisector. That's all. What is the slope of this? Minus 3 by 4. Perpendicular bisector means slope will be 4 by 3. So it must be 4x plus 3y is equal to, you may have to start. Then it passes through the midpoint of this. What is the midpoint of this? 2, 3 by 2. 2, 3 by 2 means 2 2 sa 4 2 sa 8 plus 9 by 2. 8 plus 9 by 2, 25 by 2. This is going to become the correct answer for x plus 3y is equal to 25 by 2. What I mean to say is, you must be able to have the straight lines in coordinate geometry point of view as immediately as possible. Here we require the perpendicular bisector of this. Perpendicular bisector. It has two words in it. Perpendicular. First of all, imagine the slope. What is the slope of this line? Minus 3 by 4. Its perpendicular slope is 4 by 3. Slope is 4 by 3. What does it mean? It starts with 4x minus 3y. Immediately, if you know the slope, you must be able to have this, you must be able to imagine the straight line, 4x minus 3y. Now, bisector, so it passes through the midpoint. What is the midpoint here? 2, 3 by 2. 4 2s are 8. 8 minus 9 by 2. What is that? 16 minus 9, 7. 7 by 2. So 4x minus 3y is equal to 7 by 2 is the right answer. We are ready to have the answer as we know the concept. Mod z minus z1 is equal to mod z minus z2 implies it is z lies on the perpendicular bisector of that. That is essential. So, what is the utility of this concept? You will be able to answer the questions like this. One more. Let us have a good practice of that. Modulus of z minus 2i is equal to modulus of z plus I. What is the locus of z? Z minus 2i. 2i means this is the point 0, 2. 0, 2. And this is the point 0, minus 1. 0, minus 1. Isn't it? Z plus I means you are supposed to have it as 0 minus minus 1. Z minus minus I. What is minus I? 0, minus 1. What is the perpendicular bisector of this? Equation of this is x is equal to 0. Perpendicular means y is equal to 0. Perpendicular means y is equal to something, isn't it? X equal to 0 is nothing but y-axis. What is the line perpendicular to y-axis? Parallel to x-axis. So, parallel to x-axis means it starts with y is equal to midpoint of these two. 2 minus 1 by 2 is nothing but 1 by 2. Y is equal to half. So, the locus of z is nothing but y is equal to half. Y is equal to half. Like that. So, we are ready to have the answer because we know that the locus of the form mod z minus z1 is equal to mod z minus z2 is just nothing but the locus is nothing but the perpendicular bisector of the segments joining at z1 and z2. Yes. Next one. Mod z is equal to phi. What is the locus of z? It is direct and simple. On the spot itself, you will have to have the answer. Mod z is equal to phi. Let z is equal to x plus iy. Root x square plus y square is equal to phi. X square plus y square is equal to 25. Hence, it is a circle with center, origin and radius phi. Mod z is equal to phi implies locus of z is a circle centered at origin and radius phi. Mod z is equal to k, where k is a positive number. It is a circle centered at origin with radius k. Good. Just like that. Modulus of z minus 1 is equal to 3. What is this? Z minus 1. Z means x plus iy. X minus 1 plus y. So x minus 1 whole square plus y square is equal to 9. Is a circle centered at 1 comma 0. 1 is a real part, you know. No question of I here. Is a circle. Is a circle with center. What is center? 1 comma 0. Radius 3. What is the locus of z such that z plus 2i is equal to 5? Now imagine z plus 2i. X plus iy plus 2i means x plus y plus 2 into I. Modulus means x square plus y plus 2 whole square is equal to 25. X square plus y plus 2 whole square. So again this is a circle with center 0 comma minus 2 and radius 5. And in general, the most general concept, z minus z naught is equal to k. What is this? It is just nothing but a circle with center z naught and radius k. With center z naught and radius k. You can take a z is equal to x plus iy and z naught is equal to a plus ib. It's nothing but x minus y plus I into y minus b. If you find the modulus and square it, then x minus a whole square plus y minus b whole square is equal to k square. It is just nothing but the circle with center AB and radius k. AB, the point AB is nothing but the point z naught. Isn't it? The point AB is just nothing but the complex number z naught. So it is a circle with center z naught and radius k. Like that we will be able to have. Next one. A complex number z satisfies that z is equal to tz1 plus 1 minus t into z2, where z1 and z2 are two given complex numbers and t is a real scalar. What is the locus of z? What is the locus of z? It's very simple. Z is equal to tz1 plus 1 minus tz2. It can again be taken as z is equal to tz1 plus 1 minus tz2 by t plus 1 minus t. Any problem? You can write that. So that z is the point which divides z1 and z2 in the ratio 1 minus t is to t internally. Shall I repeat it? This looks like the point z divides the segment z1 and z2 in the ratio 1 minus t is to t internally. That is, those 3 points are collinear. What are the points? Z, Z1 and Z2 are collinear. What can you say about the locus of Z? It is just nothing but the straight line joining Z1 and Z2. Z lies on the straight line joining Z1 and Z2. By focusing our attention on this locus, we are able to recollect a formula of a complex equation of a straight line joining 2 points z1 and z2. What is that? That is just nothing but tz1 plus 1 minus tz2. It is of course called the parametric equation because t acts as the parameter here. Of course, without using the parameter also you'll be able to have the equation of a straight line in terms of complex numbers joining 2 points z1 and z2. Later on we shall decide, we shall judge. So this is equation of a straight line, equation of a straight line joining the two complex numbers z1 and z2 with parameter t. You can observe. Now we shall observe general equation of a straight line. In our earlier days of coordinate geometry of earlier classes, we can recollect every straight line takes the form x plus by plus c is equal to 0 to have the standard equation. Isn't it? X plus by plus c is equal to 0 of those days. How does it become nowadays in complex numbers? It is quite interesting. Let us look at that. Let us recall that the standard equation of a straight line in coordinate geometry with in two dimensions is ax plus by plus c is equal to 0. Keeping that in our mind, we are supposed to design an equation in complex number system of the straight line joining the 2 points. In general, right? Let z is equal to x plus iy, the most general complex number. Let alpha is equal to a plus ib. A non-real complex number. What I mean to say is b is not equal to 0. It is non-real complex number. A, that is real part, may be 0 or non-zero, I don't mind, but b should not be 0. Non-real complex number. And beta be a real number. Real number. Now, let us calculate alpha z bar plus alpha bar z. What happens to the fate of this expression? Alpha z bar plus alpha bar z. It's very useful. It can be used at so many instances, of course. At so many contexts we use it. So let us have a standard outlook in our mind about this expression. There is a alpha z bar and alpha bar z. What is going to happen? Let us see. What is alpha? A plus ib. What is z bar? X minus iy. Surely, as z is x plus iy, what is z bar? X minus iy plus alpha bar a minus ib z x plus iy. ax to ax. ib into iy. ib into minus iy. Minus I square by. What is minus I square? Plus 1. So it is by. It is also by. What does it mean? 2by. 2by. So far, I could have collected, rather gathered the real part of this big complex number. Now, let me collect the imaginary part plus I into, let us see what happens. I into bx minus ay. And here ax minus by. So that ax I into bx minus ay. Here minus bx plus ay. Here ay minus bx. bx, ay and ay. Astonishing. No imaginary part. This is just nothing but 2ax plus 2by. You add some other beta so that alpha z bar plus alpha bar z plus beta is equal to 0. We can take this as the most standard form of a straight line using complex numbers. Why are you confident and sure of it? This part is nothing but 2ax plus 2by. Mind it in your mind. Let me call beta some 2c. I mean to say beta some 2c, where c is a real number. C is a real number. Then this takes the form 2ax plus 2by plus 2c is equal to 0. By cancelling 2, of course, we shall be having x plus by plus c is equal to 0, which is the most standard form of our good olden days of coordinate geometry of our earlier classes. Of course. Therefore, alpha z bar plus alpha bar z plus beta is equal to 0 gives us the most standard or general equation of a straight line. Of a straight line. Yes. Moreover, by making use of this, we will be able to have some more fundamental results also. Yes. So hereafter, what is the standard equation of a straight line? Alpha z bar plus alpha bar z plus beta is equal to 0. It is a where alpha is a non-real constant, non-real complex number, and beta is a real number. Is the most standard form of a equation of a straight line. Moreover, this part we shall be making use of in circles also. Don't forget it. Alpha z bar plus alpha bar z is just nothing but 2ax plus 2by, provided alpha is equal to a plus bi. A and b are real numbers and the complex number. Yes. Therefore, we have noticed that the general equation of a straight line is alpha z bar plus alpha bar z plus beta is equal to 0, where alpha is a non-real complex number and beta is a real constant, is the most general and standard equation of a straight line. Now we make use of this to obtain a very good condition, very useful condition for the collinearity of 3 points. What I mean to say is, if Z1, Z2, Z3 are collinear, then Z1 bar, Z1, 1, Z2 bar, Z2, 1, Z3 bar, Z3, 1 is equal to 0. How can we believe that? How can you believe that? Should you remember that? Just not necessary. How? How? Look here. Let this be the line containing those three. Then these three complex numbers should satisfy this equation. What should happen? Alpha Z1 bar, alpha bar Z1 plus beta is equal to 0. Making use of Z1. Z2 also lies on that. That is alpha Z2 bar, alpha bar Z2 plus beta is equal to 0. Now let us make use of the third point, that is Z3, also to lie on the standard form of the line. Then alpha Z3 bar plus alpha bar Z3 plus beta is equal to 0. You just eliminate alpha, alpha bar and beta among these three equations. You will be having that. Just in one word or one step you are able to achieve the answer. What should you do? Eliminating alpha, alpha bar and beta from these equations. We have Z1 bar, Z1, 1, Z2 bar, Z2, 1, Z3 bar, Z3, 1 is equal to 0. It's very simple. That is the condition of collinearity. And some others say, or some students like to use that condition like this also, as Z1, Z1 bar 1, Z2, Z2 bar 1, Z3, Z3 bar 1 is equal to 0, which is going to give us the same answer. It is just a transference of first column and second column there. No change in it. It is also 0. That is the condition for us to have the collinearity of 3 points, Z1, Z2 and Z3. One more, we can be inspired of this condition to frame the equation of 2 points, the equation of the line joining 2 points Z1 and Z2. How? Without any parameter. Previously, of course, we could have got an equation of the line joining the two complex numbers Z1 and Z2 as Z is equal to TZ1 plus 1 minus TZ2 with t as the parameter. Now we get ready to know the equation of a straight line joining 2 points z1 and z2 without using any parameter. How can we make that? Simply by looking at that z bar 1, z1 z bar 1, z2 z bar 1 is equal to 0. You can take this as the equation of a straight line joining z1 and z2 here. Yes, it's very easy to verify. You take z1 in the place of z, then first two rows become equal, answer is 0. If you take z2 in the place of z, first row and third row become equal, then answer is 0. Therefore, both z1 and z2 are satisfying this equation. This is just nothing but the equation of the straight line joining z1 and z2 also. Therefore, by framing the standard equation of a straight line as alpha z bar plus alpha bar z plus beta is equal to 0, it is just immaterial. Even if you write alpha bar z plus alpha z bar, nothing happens. It is the standard form. You can use it as you like it. This is the standard form. By making use of that, we are able to have a condition of collinearity, and by looking at we are able to have the equation of a straight line joining two complex numbers z1 and z2 without using a parameter. That is, it is non-parametric form of the equation of a line joining two complex numbers z1 and z2. It can be traced as determinant z bar 1, z1 bar 1, z2 bar 1 is equal to 0 is the equation of the straight line. Yes, let us observe some more applications. We shall now switch over to an interesting topic, complex slope of a line joining 2 points z1 and z2. Complex slope of a line joining two complex numbers z1 and z2. It is defined that the complex slope of a line joining 2 points z1 and z2 as z1 minus z2 by z1 bar minus z2 bar. z1 bar minus z2 bar. Or even you can take z1 minus z2 by mod z1 minus z2 whole bar. By making use of the properties of complex conjugates, z1 minus z2 whole bar is nothing but z1 bar minus z2 bar. It is the complex slope. By defining the complex slope, generally we take interest to have the conditions of parallelism and perpendicularity of two straight lines. Suppose two straight lines are there, say W1 with slopes, complex slopes W1 and W2. When can you say that those two are parallel? Naturally, W1 is equal to W2. Parallel lines will have equal slopes. So W1 is equal to W2, then they will be parallel. And they like to be perpendicular. Then what happens? If they are perpendicular, then W1 plus W2 is equal to 0, or W1 is equal to minus W2. And it can be derived very easily, of course, if you take W1 as z1 minus z2 by z1 bar minus z2 bar, and W2 as z3 minus z4 bar. Or suppose two straight lines are there, then automatically they have equal slopes, implies they are parallel, no problem. What about the perpendicularity? W1, W2. Amplitude of this by this must be pi by 2. And you can notice that both W1 and W2 have a unit modulus. Modulus of W1 is mod z1 minus z2 by modulus of z1 minus z2 bar is nothing but 1. Again, this is also, so that you can have that as in terms of pi, you will be able to write so that the proof is as a matter of time. Therefore, they are perpendicular. We can show that the two lines with slopes, complex slopes, W1 and W2 are perpendicular if W1 plus W2 is equal to 0. That must be kept in mind. And the two lines are parallel if W1 is equal to W2. Perpendicular if W1 plus W2 is equal to 0. This is about complex slope. The next concept, suppose there are two sets of three complex numbers Z1, Z2, Z3, W1, W2, W3. These three complex numbers correspond to 3 points which form a triangle, and those 3 points W1, W2, W3 also correspond to 3 points which form a triangle. If these two triangles are similar, similar means corresponding angles will be equal and the corresponding sides will be proportional. That is, mod Z1 minus Z2 by mod W1 minus W2 is equal to mod Z2 minus Z3 by mod W2 minus W3 is equal to mod Z1 minus Z3 by mod W1 minus W3. They are proportional and corresponding angles will also be equal. That is, amplitude of Z2 minus Z1 by Z3 minus Z1 is equal to amplitude of W2 minus W1 by W3 minus W1, like that. By making use of equality between the moduli, the proportionality between the moduli and amplitudes, you can arrive at a beautiful condition like sigma W1 in Z2 minus Z3 is equal to 0. It is a famous condition of similarity between two triangles with vertices W1, W2, W3 and Z1, Z2, Z3. Of course, this can be replaced by Z1 into W2 minus W3 sigma is equal to 0. That can also happen, and the proof is may not help us in view of the scope of time. Therefore, you can easily recollect that this condition is the condition of similarity of two triangles. If Z1, Z2, Z3 and W1, W2, W3 are the vertices of two similar triangles, then we can have sigma W1 into Z2 minus Z3 is equal to 0. One more famous and important concept we are going to learn. Pay the complete attention here. The famous, more useful, important concept regarding an equilateral triangle we are going to learn. Yes. If Z1, Z2 and Z3 are the vertices of an equilateral triangle, a symmetric result, a useful result, a famous result regarding the vertices of an equilateral triangle, we are going to learn 1 by Z1 minus Z2 is equal plus 1 by Z2 minus Z3 plus 1 by Z3 minus Z1 is equal to 0. From which we can also derive that Z1 square plus Z2 square plus Z3 square is equal to Z1 Z2 plus Z2 Z3 plus Z3 Z1. Of course, we will be able to derive this from this. Both are useful. You see, how can we get this? They are the vertices of an equilateral triangle. What does it mean? Mod Z2 minus Z1 is equal to mod Z3 minus Z2 is equal to mod Z3 minus Z1. All the sides are equal. All the angles are also equal. Therefore, amplitude of Z2 minus Z1 by Z3 minus Z1 is equal to pi by 3. Like that. all the angles are also equal. By making use of those concepts, you can arrive at this condition. Some 5 to 6 steps. It's a matter of time, and it is very, very easy to get that result proved. No problem at all. But the main concept it is under use at so many occasions in which equilateral triangles are discussed with. It's a famous condition. It can be compared with the properties of equilateral triangles in the properties of triangles of trigonometry. Yes, such a famous result it is. You can use these results as and when equilateral triangles are considered. Not only that, if in this case, if Z0 is the centroid or circumcenter, I think everybody knows that in the case of an equilateral triangle, centroid, circumcenter, orthocenter and incenter, they coincide at one point, that is centroid, of course. If at all that is Z0, in the case of an equilateral triangle, then we shall be having Z0, Z1 square plus Z2 square plus Z3 square is equal to 3Z0 square. 3Z0 square. Beautiful result in the case of an equilateral triangle. Hence, these can be thrown under the same heading. If Z1, Z2, Z3 are the vertices of an equilateral triangle, then any one of these can be used at any instant in which equilateral triangles are under discussion. Yes, it is a beautiful result regarding them. Next, one more thing. A complex number is given, of course, which represents a point on the orgone plane, and a straight line is also given in terms of complex numbers. How to find the perpendicular distance in terms of complex numbers? There has been a beautiful mechanism, of course, which is easy to recollect, which is easy to remember, which is easy to use. Let us now compare this with that of our good olden days. Suppose in coordinate geometry, a point say x1, y1 is given, and from which length of the perpendicular is required on to the straight line ax plus by plus c is equal to 0. Come on friends, let us recollect the procedure. What is the distance here? Modulus of ax1 plus by1 plus c by root of a square plus b square is given. Could you recollect? Now, the concept here is a point Z1 is given, and the line onto which a perpendicular is to be made is nothing but the standard equation, that is alpha z bar plus alpha bar z plus beta is equal to 0. Compare these two occasions. There, numerator is ax1 plus by1 plus c is just nothing but the quantity which is obtained by direct substitution of x1 y1 in the equation. Here, same thing we get. Let me call this some distance d. D is equal to modulus of alpha z1 bar plus alpha bar z1 plus beta by stop there. Here root of a square plus b square, isn't it? In the place of ax plus by, what do you have here? Alpha z bar plus alpha bar z. You remember, we have noticed, we have put that particular quantity in our mind. What is alpha z bar and alpha bar z? Alpha z bar plus alpha bar z is nothing but 2ax plus 2by, isn't it? Okay, if you have 2ax plus 2by here, what is the denominator? Root of 4a square plus 4b square. If you get 4 out, 2 into root of a square plus b square. What is root of a square plus b square in this instant? Is it not mod alpha? S of course, hence it is 2 into mod alpha. So many units. This is the beautiful result which can be traced simply by matter of comparison with that of the result which we could have already had in our coordinate geometry, isn't it? S of course. This is the perpendicular distance of the point Z1 from the line alpha z bar plus alpha bar z plus beta is equal to 0. That's all.